Hello and welcome back to Abstract Linear Algebra, the video course where we extend our linear algebra knowledge. And in today's part 44, I show you how we can use the knowledge of the Jordan normal form in applications. In particular, we will consider the so-called matrix exponential, and we will see that we can calculate it for any matrix by using the Jordan normal form. However, as always, before we start with the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. Your support makes it possible that I can create a lot of mathematical videos about different topics. And moreover, as a supporter, you can get a lot of perks, which you can find with the link in the description. Okay, then without further ado, let's immediately start discussing the Jordan normal form again. In fact, we have already used a lot of videos to prove the fact that every matrix A, which is a square matrix with complex entries, has a Jordan normal form. This means we can always find a basis in Cn such that our matrix A has a matrix representation with respect to this basis that looks like a Jordan normal form. And essentially this change of basis is given with an invertible matrix X. So the conclusion is that X inverse AX is a Jordan normal form. And we have already learned that in the columns of the matrix X, we put generalized eigenvectors of the matrix A. For that reason, in the Jordan normal form, we always find the eigenvalues of A on the diagonal. And indeed, how often one eigenvalue is repeated on the diagonal is given by the algebraic multiplicity. So if you know all the eigenvalues of A and the corresponding algebraic multiplicities, you know the whole diagonal of the Jordan normal form. Moreover, we also know that the Jordan normal form is a special upper triangular matrix. This means there are only non-zero numbers above the diagonal, and we also know we don't have many of them. More precisely, we have proven that only the number 1 can exist directly above the diagonal. However, for our next conclusion, we don't need these details because we just need these two pieces of information. So let's formulate it as an important corollary. What we get is that the determinant of A is already determined by the eigenvalues. This is easy to see because the determinant does not change if we substitute A by a similar matrix. This immediately follows by the fact that the determinant is a multiplicative function. Okay, and now what we have here is a Jordan normal form, which is a triangular matrix. Which means the determinant of this matrix is given by multiplying the whole diagonal. This means we just have to multiply all eigenvalues counted with respect to the algebraic multiplicities. Hence, we could just write the product where we have j going from 1 to n of lambda j, where lambda j is an eigenvalue of A. And again, as before, we have to repeat a given eigenvalue if the algebraic multiplicity is greater than 1. Therefore, we always have a product from 1 to n. So this is our whole result, and you can remember it. No matter how complicated the matrix A is, the determinant is always given as the product of the eigenvalues. Indeed, we already knew that for a diagonalizable matrix A, but now we know it for all complex valued matrices. Please note this also means if you have a matrix with only real values inside, you can use the formula as well, but maybe the eigenvalues are complex numbers. But it means that the product of these complex numbers is a real number again because it's the determinant of A. And at this point I can already tell you, if we have a sum instead of a product symbol here, then we talk about the so-called trace of A. However, this trace is something for another video, because here I first want to show you more about the Jordan normal form. In fact, we already know that such a Jordan normal form can be split into two parts. We have a diagonal matrix and a so-called nilpotent matrix. To see this, let's look at an example where we have two Jordan blocks. This means our matrix has exactly two different eigenvalues, in this example 4 and 6. So you know, these two things is what we call Jordan blocks, and inside a given Jordan block we find the so-called Jordan boxes. And for seeing the Jordan boxes, it depends where we find the ones above the diagonal. So in this case here, we have two Jordan boxes in each Jordan block. And now the important part is that we can distinguish the diagonal and the nilpotent part in each of the boxes. So you see, this is quite simple. We just have a sum of two matrices. For the diagonal part, we just delete the ones we have above the diagonal, and for the nilpotent part, we delete the diagonal. So this is all. We just have a matrix D and a matrix N, and we calculate the sum to get our Jordan normal form back. And now the question I want to ask you, do these two matrices D and N commute? So we just have to calculate D times N and see if this one is the same as N times D. And now the good thing is that this multiplication is not complicated at all because it breaks down to the Jordan boxes. So indeed, when you see the matrix product here, you essentially just have to multiply the Jordan boxes that correspond to each other. So for example, you have to multiply this diagonal box to the box that just has a 1 here. But obviously, the first part here is just 4 times the identity matrix. Hence, obviously, the result is actually the same when we consider the different order in the multiplication. And obviously this works for every other Jordan box as well, because the form of the Jordan box is always the same. So in total, we immediately get that D times N is the same as N times D. So the result is both matrices commute. And this is an important ingredient of our Jordan normal form because we can use it for the so-called matrix exponential. This is a matrix construction which works for every square matrix A. And the resulting new square matrix is what we call exp of A. And the construction is like you know it from the exponential function. First you start with the constant 1, which is the identity matrix in our case. Then comes the linear factor, which is the matrix A itself. And then 1/2 the matrix squared plus 1 divided by 3 factorial times A cubed. And this just continues, so you see we have an infinite series of matrices. Or in other words, you could say in each entry of our matrix we have a series given, and this one is a convergent series because the exponential function is a convergent series in the complex numbers. So the result is that this infinite sum here is always a well-defined matrix. And obviously the short notation for the whole series can be written as 1 over k factorial of a to the power k. And now you might already guess that this power ak can be transformed into a Jordan normal form. In fact, this is quite simple if we already have the Jordan normal form J for A. This means we have xj x inverse to the power k. And there you should see we can just put all the matrices together, and in the middle x inverse and x will always go to the identity matrix. So what essentially remains is just x times j to the power k times x inverse. And since this calculation works for the whole sum in the matrix exponential, we can use it immediately. So we have x times the exponential of the Jordan normal form j times x inverse, so our matrix exponential here is transformed in the same way as A. Therefore, in order to calculate the matrix exponential, we just have to calculate the matrix exponential of a Jordan normal form. However, for this one, we already know that we can split it into two parts, namely the diagonal matrix and the nilpotent matrix. So what we get is a sum of two matrices inside the matrix exponential, and now you might think that we can use the standard exponentiation identity to split it up into a product. However, the thing is that this fundamental rule of the exponential function only holds if the components commute. In fact, you can check my real analysis course to check that the proof requires that the real numbers commute. However, now the good thing is that D and N also commute, so we can do the proof like in the real numbers and get our identity. However, please be careful, in general this is not correct, it's only correct for commuting matrices. Hence our result here is that we have the product of two matrix exponentials. And now you see, the only problem while calculating a matrix exponential is that you need to know all the powers of the matrix A. But of course, powers are really simple for a diagonal matrix, because all the powers just occur on the diagonal again. So the first part here is not a problem at all, we can immediately write it down. Therefore, the only powers of a matrix you actually have to calculate are the powers of the nilpotent part. However, the term nilpotent actually means that the powers are eventually equal to the zero matrix. So for this one, you only have to calculate a finite number of powers. Therefore now, instead of calculating an infinite series of a lot of matrix multiplications, now you just have to calculate a finite number. So you see, the power of the Jordan normal form makes this matrix exponential computable. Of course, at this point you might ask, why do we need this matrix exponential at all? But this you can find in my ordinary differential equations course. Because there it turns out that a solution space for a system of differential equations can be written with the help of the matrix exponential. And there obviously it's really helpful to actually know how to calculate this whole thing. Therefore, please check out the ordinary differential equations series to learn more about this matrix exponential. Otherwise, I would say for this video course we have talked enough about the Jordan normal form. With the next video we start with another matrix decomposition. So I really hope I meet you there again and have a nice day. Bye bye.